RAID, or redundant array of independent disks, method of combining multiple physical disks to act as a single logical unit. It improves performance, fault tolerance, and storage reliability. It is used to enhance data availability and system performance in high-demand environments. There are two types of RAID: hardware RAID, which uses a dedicated RAID controller for better performance. Software RAID is managed by the operating system, more flexible but with some performance overhead. Why RAID is needed? Redundancy prevents data loss in case of disk failure. Performance increases read-write speeds using data stripping. Scalability allows adding more disks without disrupting operations. Reliability ensures database consistency and uptime. Types of RAID levels. RAID 0. Data is split into blocks and distributed across multiple disks. Its advantages: it has high read-write performance. It uses full storage capacity. Its disadvantages: no fault tolerance, which means if one disk fails, all data is lost. This is used in applications where speed is critical. For example, gaming, temporary storage. RAID 1 is also known as mirroring. This is how it works. Identical copies of data are written to two disks. Its advantages: high fault tolerance, which means if one disk fails, the other remains functional, and easy data recovery. Disadvantages are that its storage efficiency is 50% since the data is duplicated. It is used in critical applications requiring data redundancy, for example medical records, financial systems. RAID 2. Bit-level stripping with ECC. It uses bit-level stripping, meaning data is broken down into individual bits and spread across multiple disks. It uses Hamming code error correction to detect and correct errors. Its advantages are that it provides error correction capabilities, and it is good for systems that need high fault tolerance. Its disadvantages are that it is very complex to implement, high overhead due to additional error correction bits, no performance benefit over modern RAID levels. It is rarely used today due to inefficiency. RAID 3, which is byte-level stripping with dedicated parity disk. Here, data is divided into bytes and striped across multiple disks. A separate disk stores parity information for error recovery. Its advantages: better fault tolerance than RAID 0. Faster sequential read-write performance. Its disadvantages: parity disk bottleneck, which means that all writes require updates to the single parity disk, slowing down write speeds. Not good for random input-output operations. It is used in high-speed applications where large sequential reads are common, for example video streaming and scientific simulations. RAID 4, which is block-level stripping with dedicated parity disk. Here, the data is striped at the block level across multiple disks. A single disk stores parity data for error recovery. Its advantages: faster read performance due to stripping. Provides fault tolerance by storing parity. Its disadvantages: parity disk bottleneck. It is used in systems requiring high read speeds and moderate redundancy. Example data warehousing and archive storage. Then, RAID 5, which is block-level stripping with distributed parity. Here, the data is striped across multiple disks. Parity is distributed across all disks instead of using a dedicated parity disk. If one disk fails, data can be reconstructed using parity from other disks. Its advantages: good balance between performance, storage efficiency, and redundancy. Faster reads than RAID 1 due to stripping. Its disadvantages: it has a slower write performance due to parity calculations. It is used in web servers, database servers, and file storage systems where high read speeds and fault tolerance are needed. RAID 6, which is block-level stripping with double distributed parities with two parity blocks and can handle to simultaneous disk failures, making it ideal for mission-critical applications. It has a higher fault tolerance than RAID 5. It requires more parity calculations, leading to slower write speeds, and requires more storage. It is used in data centers Cloud storage, which is suitable for large-scale database storage. Choosing the right RAID level depends on your performance needs, redundancy requirements, and budget. Hence, RAID is essential for database reliability and performance. Each level has its strengths and weaknesses, but the right setup can ensure your data remains safe and accessible.